Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem freedom trail. So they give us a pretty long explanation here. They give us some context that's really not necessary, so I'm going to skip over that. Let's just focus on the example here because it does make things pretty simple for us. So imagine we're given a string, and this string is actually placed on a wheel where the first character in that string is at the top, aka like 12 o'clock if this was a clock, and then the second character is going to be here, third here, and it's just going to keep going like that until it loops all the way around. Now, it could have an arbitrary number of characters in the string, but the only thing that really matters is the relative position of these characters, because what we want to do with them is actually spell the second word that's given to us. This is just GD, and we want to count the number of moves it takes for us to spell that word, and we actually want to minimize that, minimize the number of steps it takes. So let's walk through this example. We start here. To spell a single character of a word, even if we're already at the character that we need, it does take us a move. So I'm just going to keep track one so far. And then from here now, we're trying to spell the second character, D. Now we have a choice. We can either stay where we are, that doesn't cost us anything. We can either move to the left, which costs us another move, or we can move to the right, which costs us another move. I'm going to choose to move to the right. So far we've done two moves. We're over here. That's obviously not the character that we want. So what should we do? Well, I'm going to move to the right once again. That's going to cost us another move. And then to actually use this character, this is the character we're looking for, D. To use this character is going to cost us one more move. So that's going to be 4 total. And that's the result. That's the best way to minimize this. If we were to have gone the other way, it's going to take us a while to land at a D. So immediately, if you think you're being smart, if you think you're being clever and you're trying to skip the brute force solution, you're going to run into some problems, and let me kind of show you a counter example of why that is. Suppose this is our clock or whatever, and I know it's not drawn exactly in the shape of a circle, but suppose the word that we're trying to spell is ABX. Now, like I said, if you're trying to be smart, you're trying to be clever, or you're trying to be greedy, you might say, okay, we're already at A, great, and now we want to go to B. There's actually 2 B's in this circle. Which one do you think we should go to? Probably the one that's closer. That would seem obvious. It takes us one move to get here, and then we use the B, and now we're trying to spell X. Okay, to get to X, it's going to take 1, 2, 3, 4 moves, or we could go the other way, 1, 2, 3, 4, 5 moves. Either way, it's going to take us 4 or 5 moves to get there. Okay, well, maybe we can initially take the long path. We can take 1, 2 steps to get to the B, and then to get to the X is actually just 1 step. So this turns out to actually be the optimal solution, even though it's not the greedy solution. That's why we can't be greedy. So let's go back and think about the brute force approach here. So obviously, if we're at a certain character, like this is the character we're trying to find in the word we're trying to build. If we're already there, we should definitely use that character. It doesn't make any sense to, there is a second A over here. Why would we travel there to just reuse the exact same character? There's no sense in doing that. So we use this. But now when it comes to the next character, we want to find a B. We're over here though. So which B do we go to? In this case, the input has several B's. It has 3 B characters. Which one should we go to? Well, we do have to brute force it and try all 3 of them. But even in doing that, it's not as simple as you might think, because at least the way I first thought about it is, even though there's 3 B's here, that doesn't mean we have 3 choices. I'm smarter than that. We actually only have 2 choices. We can either go left in the wheel or go right. But if you do that, like suppose we went here, we're at A, then we go to E, and now we have 2 choices once again. We can either go back to A or we go down to B. And now this path is kind of just going to go forever, right? It's going to go to E, then it's going to go back to A. So we get stuck in an infinite loop doing it this way. So it doesn't make any sense to think of it in terms of 2 different moves. It's easier to actually identify all of the B's in the entire ring and then try all of those possibilities. And the reason that doesn't actually make our solution more inefficient than you would think is because in terms of the subproblem, like what parameters are we going to be passing into this brute force solution? And by the way, this is going to be done recursively. So I'm going to kind of gloss over a lot of the recursive logic because this is a hard dynamic programming problem. I would definitely recommend solving some easy or medium ones if you're not familiar with what I'm about to talk about. The idea is we really only have to keep track of two things. This is the key we're trying to build. So the pointer, I'm going to refer to that as K. We keep track of the K pointer, the character in the key that we're trying to currently build. Also, we keep track of R, the index of the character in the ring that we are currently at. So this is our subproblem. This is what we're trying to compute. Right now, when we're at the second character, this subproblem is going to be 0. Let's say 0 is the index of this character, and 1 is the index of the key character that we're currently at. So we have three choices here. We can go to this character over here, this B, which let's say is at index 1, and we can go to this character and this character as well. And I won't draw out that portion, but that's the idea here. A subproblem is defined by the ring index that we're currently at and the key index that we're trying to arrive at. Even doing this recursive part isn't super smart. Before we even make that recursive step, what we should first say is this: how many moves is it going to take us to arrive at this B? Well, of course, that distance is just 1, but it becomes less clear for some of these other ones. Like this one is pretty clear. How much distance is it going to take us to get there? It's going to take 2. What about this guy? It's not super clear by looking at it. It looks like if we go this way, it's 1, 2, 3, 4. If we go the other way, it's 1, 2, 3, 4, 5. So we kind of have to try both ways. We at least have to compute the distance going one way and the distance going the other way and find the minimum of those two. This is the case where we can be greedy because we're trying to arrive at this character. We're considering what if we were to go to this B instead of these two? And of course, why would we take the long route to get there rather than the short route? It doesn't have any benefit for us to take the long route. It doesn't matter what characters are in between because we're only trying to find the B character. I think it's worthwhile to mention how we're going to compute this. So quickly, let's remember that this is actually stored as a string. So if we were to draw this out, we'd have the ring. This is the ring here. This middle B, if we want to compute the distance from here going this way, obviously, or we can go the other way, which would be going all the way to the end of the string and then back here. Let's first just start with the easy way without having to go in a circle. The easy way would just be taking the index here, which let's assume is I. Let's assume this is J. We would just take the difference. We don't know necessarily which one of them is going to be bigger. We could have an if statement to do that, but the easiest thing would just be take the absolute value of the distance, I minus J. Okay, now what about going the other way? What about going here and then going to the character? That's a little more annoying to compute. The easiest way to do that would just be to, first of all, look at it. If we've already computed this distance, what we're really saying is what are the other remaining characters? So in other words, we can take the length of the ring and subtract it from this value that we already computed. Let's just go over the example real quick. So let's say this is index 0, this is 1, 2, 3, 4. We'd take the difference, we'd get a distance of 4. We see that the length of the entire thing is 9. We say 9 minus this, which is 4, is going to be equal to 5. The math does check out because it takes us one jump to get here, 2, 3, 4, 5. I won't go over this, but if you want to try the same thing, suppose instead of starting at the beginning of the ring, we were to actually start over here, you can try that on pen and paper and you'll find that the math does indeed work out. That's not too bad. Just to summarize, from here, now to get to the next character, we'd take 3 branches to each of these B characters, and from those, we would try to figure out which one of them is going to return the minimum result. And of course, from each of them, it's going to be its own subproblem. So basically from this B, we'd find obviously there's only a single X in the input. The distance from there is 1. The distance from here is 2, and the distance from here I think is 4 or something like that. I think that's more or less enough intuition for us to get into the coding explanation. So now let's code it up, and I guess I didn't mention that we are going to use caching in this problem just because the brute force is going to be very inefficient. as you're going to see in a second. And I'll also go over the time complexity of the caching solution. So like I said, we're keeping track of two variables, the index of the ring and the index of the key. So the base case obviously would be if we've already filled every character in the key, aka the k index has reached the end of the key. So k is equal to length of key. And in that case, we just return 0. Otherwise, we're trying to compute the result of this subproblem, which tells us the minimum number of steps to fill in the rest of the key if we're starting from this index. We're going to call that result, we're going to initialize it to a very large number. So we'll return result like this. But now it's time to actually compute it. We can do that like this. We're going to first go through every character in the ring. I'm going to do that like this. IC in enumerate the ring. Now, technically, you don't have to do it like that. You could map every single character in the ring, every unique character, to all the indexes that it shows up at. And then you wouldn't need to loop over the ring. It doesn't really make a huge difference in this problem because the same character could be repeated in the ring a lot. And the length of the ring isn't that long, so it doesn't make a ton of sense to do that. In this case, it doesn't really improve the overall time complexity, but it is an optimization you could make if you wanted to. But we're not going to do that. Since we're just going through every character in the ring, we don't necessarily know that this character is the one that we're looking for. So let's verify that it is. If this character is the character that we're looking for, which is at index k within the key, then let's do the recursive step. So how do we do the recursive step? First of all, let's calculate the distance between this character, the character that we are targeting, and the index that we're currently at. How do we do that? So we're currently at this index in the ring, but this is the index that we want to arrive at. Well, that's what I talked about earlier. You might have forgotten, so let me quickly go over it again. We're going to take the minimum of 1, the absolute value of r minus I. This is the distance between the two indexes. And the other one is the length of the ring minus what I have up above. And this would tell us the distance if we were to go around the ring. And the minimum of these two is going to be set to, let's say, a variable that I'm going to call the minimum distance. Okay, with the minimum distance, the computation that we're going to do here, obviously that's the number of steps it takes us to get to that character that we are targeting. Remember, that's the character we're looking for. So we're going to take that distance plus 1, because it takes us a step to actually use the character even if we have arrived there. So that's where this math comes from. It could be possible that we do have some characters remaining. So this is where the recursive step comes in, plus the result of the subproblem, the remaining characters. So to pass in the new parameters, r tells us the index that we're at in the ring. Obviously, we are now at index I because we're at that character. So that's what we pass in for the ring index. And for this index, we just pass in k plus 1 because we just filled the k character. Now we're going to the next character in the key. This is the possible result, but we don't know if it actually is the result. The only way for us to know that is to take the minimum of this as well as the current result. So I'm going to do that just like this. So this is pretty much the entire code, at least of the brute force solution, but it's pretty easy to go from the brute force to the caching solution. But first, let me finish it up by returning the result of the helper. How do we call helper? Well, we're starting at index 0 for the ring, and we're starting at index 0 for the key. To quickly optimize this solution, we can create a cache. I like to use a hash map for that, and then we can check up here if this RK has already shown up in the cache, just return the result that we already computed. If it hasn't, right before we return down here, let's make sure to cache the result just like this. So this is the entire code. It does look like I missed a comma over here in the min function. That's pretty easy to do, but let's go ahead and run this to make sure that it works. And as you can see, it does. It's pretty efficient. Let's analyze the overall time complexity. Obviously, the number of subproblems that this helper is going to potentially solve is going to be r times k. So the overall time complexity initially you might think is r times k. But recall that we do have a loop inside of this, which is going to iterate r times. So this is actually r squared times k. That's the overall time complexity. The overall space complexity is going to be indeed O of r times k, because that's the number of subproblems that we will have cached. Now, it is actually possible to optimize this to be space-wise just big O of k. And let me show you how to do that with the bottom-up approach. And believe it or not, this problem is actually easy to translate from this to the bottom-up approach, at least the way I like to do it. And I'll show you why I like to do it that way. So the general way to go from the recursive solution to the bottom-up solution is to first look at the dimensions of the cache. Remember, it was r times k. And so then you draw out that grid. I'm going to take this part and put it on the left side, A, B, X, and then this is going to be a row. So I'm just going to draw out this grid. It's not going to be the cleanest, but the idea should be relatively clear. So here, let's have the A. Here, let's have the B, C, C, B, A, X, B, E. And I'll have like a top layer over here. Sometimes I like to use that as like the default value. So before you even start to fill this grid in or even think about how to fill it in, you have to first remember, what does this position or this position or this position represent? What does it represent? Well, what did it represent in the recursive solution? Remember, when we were at the last index, that's our base case. They call this bottom up for a reason. Let's start at the bottom. This position tells us if we are currently at this character, what's the minimum number of steps it's going to take us to build this substring? Well, it's basically the distance from here to the nearest x, which in this case is going to be 1, 2, 3, and then plus 1 to actually use the character. So it's going to be a 4 here. We could do that for every single one of these. So for this one, I guess it's going to be 5. This is going to be 6. This is probably going to be, well, actually, I think this one is going to be 5 because the steps here is just 4 steps. And then this is going to be 4 probably. This will be 3. This will be 2, and this will be 1 because we're already at the character and we just need to actually press it. This will be 2 because it's pretty close this way. And then this will be 3. Now, this was the easy part, but now when you try to fill in the next row, it might be a little more complicated, right? Because remember, what does this position represent? Let's think about it. It represents, if we're starting here, if we're at this index, it tells us what's the minimum number of steps it would take to build this substring. Well, first things first, just like the recursive solution, we have to find what are the B candidates. Well, there's a B over here, there's a B over here, and there's a B over here. There's 3 different Bs. To get to this B, it takes us 1 plus 1 to actually press it. So I'm just going to do the math down here. 2 to get to this B and press it. So that's what it takes to fill in the B. But what about the X? Well, if we're over here now, we're basically asking how many steps does it take to fill in X from this position? Well, didn't we already compute that somewhere? It looks like we computed that over here, right? So that's what this grid is for. The intersection of this and this tells us what we're trying to look for. So this will be 2 plus 5. That's one possibility. Now, what about the second B over here? It takes us 4 steps to get there, plus 1 to actually press it. So that's 5. And then from here, now we're just trying to fill in the remaining portion, which is just the X. And we know that value is down here. It's a 3, so 5 plus 3. Among these two, obviously this one is the minimum, and I'm pretty sure it's going to be the minimum even if we were to try this one as well. I don't want to spend all day here filling in the rest of this grid, but you're more than welcome to do that on your own. And I want to quickly clarify, I guess, the way we're doing this right now is bottom up. We are going to have to reverse through the key in reverse order. I think it is possible to solve this problem by reversing top down, by going from left to right in this string. But it's going to be very, very different, and I just don't think it's worth doing. If you want to spend your life doing that, you can definitely go ahead, but it's going to be really weird. It's going to change the context of this problem a lot. It's basically going to say, instead of starting, like we know that we're starting at the center of this ring, at the top of the ring, but if you're going to build this thing in reverse order, you actually have to start at the last character and then build this thing in reverse order. It's not really worth doing it like that. That would be the way to build it, like first build this substring, then build this substring, and then build this one. I would prefer to build this substring, then this one, and then this one. It just makes things a lot easier, and believe it or not, the code is going to be trivial. One thing I haven't talked about is the space complexity. This one is still big O of R times K. How do we optimize it? Well, before I even mention that, I want to say that I guess the way I drew this, we actually don't need this first row since we are going to build the bottom row and then the next one and then the next one. What we're going to assume is that there's a row below this one that is kind of just zeroed out. That's our base case, similar to the recursive solution, where if we reach like the end of the key string, it takes us 0 steps, obviously, to build nothing. If you notice, to build this row, we only need the previous row in memory. And that's going to stay true for this row as well. To build this row, we would only need the previous row because it tells us how many steps to build the remaining portion of the substring. So the optimization comes from the fact that we don't need the entire grid in memory. We only need up to 2 rows in memory at a time. Therefore, the memory complexity is going to be big O of K. Let me show you how to code this up. It's going to be pretty easy. I'm going to actually leave the recursive solution shown down below. And the reason for that is because it's going to make our life so easy. This is why I like to do dynamic programming problems in reverse order. A lot of people don't like it, but just watch how easy our life is. We're going to declare our DP array. So this is one row of the table I showed you, and that kind of makes me realize, I think I just mentioned that the space complexity is big O of K. That's wrong. Sorry, it's actually big O of R because obviously this row is of length R. Then we're going to iterate over every character in the key in reverse order. It's pretty easy to do for K in reversed range of the length of the key. I know that's multiple functions stacked up on top of each other, but that's, I guess, the most readable way to do this in Python. Now, the current row that we're trying to build, we can call it current DP or next DP, whatever you want to do. That's up to you. I don't think the names are the biggest deal. First of all, the 0 that we returned in the recursive solution is kind of like the base case up above. That's why I initialized this to all zeros. Now, when we initialize the result, before we compute it, we set it to infinity. That's the same reason why I'm going to set this to a row full of infinities. And it's going to be of the same length as the other one up above, of the same length of the ring. So now we're just going to go through every value, every index in here. So for R in range length of the ring, we're trying to compute every value in here. So now that we have our K and we have our R, the rest of the code inside of this loop is going to be pretty much the same thing that I have down here. And for that reason, I'm just going to turn my brain off. I'm just going to copy and paste this code, go up above, and then just change some variables around. So watch this. I'm going to say for every index character in the ring, let's check. Is that character equal to the current character that we're trying to get right now? If it is, then let's get the minimum distance between both of them. I don't even have to make any changes to this code, do I? It's the exact same. To compute the result, this part we are going to have to change a little bit. The result that we're computing right now is in next DP. It is going to be next DP of the current R, the current character in the ring that we're at. So we're trying to find the minimum distance to compute the remaining portion of the key if we were to start at this index. That's what we're trying to minimize here. And to get the minimum, we have to take the minimum of itself. So since we changed that, we're going to change that here as well, plus the minimum distance plus 1. This part does not change. The helper definitely does change though. Before we needed a recursive function to get the result of the subproblem. But with bottom-up dynamic programming, we don't need that. We actually store the result of subproblems within our DP array thing here. The fact that this is a K plus 1 tells us we're looking at the previous DP row. So that's why we're going to change this to just DP of I. Remember up here, what this IC means is that if we're at index R and then we're going to travel to index I, it took us this many steps to do that. And so now from index I, we're trying to compute the rest of the subproblem. That's what this is. Now, after all of this is done, after we've fully computed next dp, we're going to then update it and set dp equal to next dp. Then we're done with that. Now, what do you think we're gonna return? Obviously, it has to be some value from the dp array. Well, just like down here, look, we started at index 0 for r. What do you think we're going to return from dp? Probably the value at index 0, because that's where we started from in the ring. So starting from that index, we want to know what's the minimum number of steps to compute the entire key. This is the whole solution. The space is obviously optimized. Let's run it to make sure that it works. As you can see, it does. The memory is definitely more efficient. It looks like the runtime is less efficient, but I think that's just due to the nature of this problem. In the recursive solution, we probably weren't computing every pair of RKs. In the bottom up, we are. It doesn't change the big O time complexity, but obviously it does make a difference when it comes to the actual runtime. If you found this helpful, check out Leetcode.io for a lot more. Thanks for watching, and I'll see you soon.